This lecture is about the Kalman filter. The Kalman filter allows us a way of estimating and predicting the internal states of a state space representation. It's a fantastically useful algorithm that exists in many forms of applications around the world. So for instance, any form of airplanes or helicopter or drones or whatnot will have a Kalman filter dictating how it behaves in there. You will also find the Kalman filters in many forms of economic transactions, traffic flow controls, train controls, whatever you can think of, there will be a Kalman filter there somewhere. The idea behind the Kalman filter is basically a conditional expectation. You wish to estimate what is the best possible guess of your states at time t plus k, given that you have observations up to time t like this. So that is, I have observations of the output all the way up to time t, and I would like to know the internal state. So if I select k equal to 0, I am trying to determine the states at time t given observations of the data at time t. That will be one of the cases that we need to address. If I have observations of the output, so I have y of t, and I would like to know x of t. This is this estimate. So it's the estimate of the internal states t given information y of t all the way up to time t. If I select k being larger than 0, then it will be a prediction of future events. If I select k to be less than 0, it will be an interpolation of past events. Just as in the case with recursive least squares, we also want to form our conditional expectation recursively so that we update our systems as more data comes along to allow for a more efficient implementation. So I would therefore like to find a way of formulating this conditional expectation, but updating it so that I will take the old data, like this, as well as the most recent sample, and make a recursive formulation such that I will only adapt changes due to the recent sample. The way you do that is that you extend the conditional expectation formula that we had before. Notice here that this is the conditional expectation of the states given observations z. If you think of this as z, whereas you think of this as y, you see that this is nothing but that I'm saying that x of t plus 1 should be equal to x of t hat plus some form of scaling, let's call that the Kalman gain. Not surprisingly, that is exactly what we will end up with, times some form of error, which is the expected value of yt minus my estimate of yt given t. And as you can see, this is exactly similar to the formulation of the recursive least squares that we discussed earlier. However, we will now also express the conditional variance using a recursive formulation, as this will be useful for us. So basically here we have all the things needed for the Kalman filter. And the thing that is remaining, that is also the main pain point of the Kalman filter, is the notation. So bear with the notation and try to write down what the different parts are and focus on what they are. If you understand the notation, you will basically understand the Kalman filter. Okay, so let me pick my states like this, and y as I told you, and z like I told you like this. So that means that I can express this form. So this would be the conditional expectation of x of t given t. So now I picked k equal to 0. Which will be the same thing as the expectation of x given the observations up to time t minus 1, as you can see here. I need the covariance matrix between x and y given z. That is the same thing as saying the covariance matrix between x and y given the observations up to t minus 1. That is this covariance matrix. I also need the variance of y, meaning the current sample, given the earlier samples. That is this covariance matrix. And as I noted, this is the conditional expectation of yt given that I have data all the way up to t minus 1. I will gather these two and call it the Kalman gain, and I now have the full expression that I'm looking for. Of course, I'm not done here. I need to define the updating of the different parts of this. So let's begin with the x of t given t minus 1. I can use the expression of the state space representation like this. That will give me x of t plus 1 given t and y of t plus 1 given t that I need to express this formulation. So now I need the covariance matrices to proceed. To do that, I use this second conditional expectation, inserting the notation for these. And as I said, this is the problematic part, keeping track of the x and the y's and the t's and the t minus 1s. If I just use the notation, I will move from this one equation to this equation. I will recognize that I can use the k notation here, and I will rewrite it like this. I will introduce the error, that is the difference between the true state and my predicted state, and the error of the output, which is difference between the actual output and the predicted output like this. This is my tilde notations. So you notice that this is the same thing as the variance of the errors here. Next, I recall my state space representation, as well as the predicted form that I used before. If I insert those, I can find a formulation of what my error in my state space representation will be, and my error in my output representation will be like this. Notice that the variance of this is not going to be anything but the expected value of x tilde, like this, which if you recall from chapter 2, will give us that the variance can be expressed in this way. Similarly, I can express the variance of the output error like this, and the cross error like this. And that is actually all there is to this. If I gather all these equations up, I get the update of my states. This is my state estimate of x of t given t. This is my update of my states. This is the Kalman gain that I'm computing, and these are all the covariance matrices. The only thing remaining is the setting of the initial conditions. I will set my initial state as the expected value of this first value, giving the variance here as the expected variance of that value. That means to say that if you do have a very good feeling for the initial state of your system, say that I'm using the A1 parameter that we discussed in the previous lecture, try to estimate that, and I have a very good estimate saying it is 0.59 to 0.61 or something like that. That means that I have a very good estimate of the state, then I should pick my V0, the variance of this estimate, to be low. That means that I'm conserving, allowing it to change very slowly. However, as in the case that I showed you before, when I had no idea and I just set the initial state to be 0, I basically don't trust my initial state at all. Then I would like to select my V0 large, meaning that I want to neglect my initial estimate very quickly. So if I select V0 large, I will very fast converge to the new value, but I will also have a large overshoot. If I select V0 small, I will basically trust my initial estimate very much, and I will very slowly converge into the new values like this. This also means that if you have made, say, an ARMA model of your realization, and then you have fairly good estimates of those that you trust quite a bit, you can select your initial states of your Kalman filter using those values, and you can select then the variance as the variance of the residual, thereby setting the variance in some sense scale to the error you're expecting it to have. You will probably need to fiddle a bit with the initial values to get it to converge quick enough, but you should then expect your parameters to be able to follow seasons as they change, which would not be possible for your other system to do.